Welcome to Math260, Lesson 11, Matrix Vector Equations. In previous lessons we learned how to multiply matrix times vector, and we're going to take advantage of this for systems of equations with this lesson. So let's get started. When we multiply a matrix containing numeric entries by a vector of unknowns or variables, we get a linear combination of those unknowns. For example, here I have a matrix where the aij's represent numbers and the x's represent variables. And by the way we multiply matrix times vector, we do the dot product view. The dot product of the first row with the vector of variables would give a11, x1, a12, x2, etc. on to a1n, xn. And notice the length of the vector has to be the same as the number of columns. And so this gives me a linear combination of the variables, where the a's are constants and the x's are the variables. When I do the second row, I get a different linear combination of the variables. And so here's an example with a numeric matrix with variables x1 through x4. If I do the matrix times vector operation, I get 5x1 plus 2x2 minus 3x3 plus 4x4 for the first entry in the result. I get x1 plus 0x2 plus 4x3 plus 7x4, so that's the second entry in the result. And the third entry in the result is given by 3x1 plus 4x2 minus 2x3 plus 1 times x4. This is useful when we want to model a system of equations. So if A is an m by n matrix, m rows and n columns, and x is a vector of n unknowns, so the vector x lives in n-dimensional space, and B is a vector that lives in m-dimensional space, that's the number of rows, then the matrix vector equation Ax equals b represents a system of m linear equations, one for each row, in the n unknowns, that must be satisfied simultaneously. We're looking for a single vector x that satisfies this matrix equation, matrix vector equation, and that means it will have to satisfy all of the linear equations. For example, if I have this matrix vector equation, that means that 5 times x minus 3 times y plus 4 times z must equal 8. That's because the result here is a vector, and two vectors are equal only when their corresponding elements are equal. The second dot product gives me the equation 1 times x plus 4 times y plus 7 times z, that's a plus 4y, must be negative 4. And the third dot product says that 3x minus 2y plus 1z equals 6. And so this matrix vector equation is satisfied only when we find values of x, y, and z that satisfy all three of these equations. And that's the beauty of this compact form. It encodes a system of equations that need to be satisfied together. But remember, one way of considering matrix times vector is as a linear combination of the columns of the matrix, and that gives us another way to look at the matrix vector equation. So here's the same setup. We have matrix times vector, but now we view it as a linear combination of columns. I'm going to have x1 times the first column plus x2 times the second column up to xn times the nth or last column of the matrix. So viewing it this way, Ax equals b is satisfied only if the linear combination of the columns, we can find x's so that the linear combination of the columns gives the b vector. So in more symbolic form, if I let u1 represent the first column of the matrix, u2 represent the second column of the matrix, etc., up to un representing the nth column of the matrix, we have a new form represented by the same matrix vector equation AX equals B, but it also represents this linear combination x1 times u1 plus x2 times u2 up to xn times un equals b, or finding a linear combination of a set of vectors that gives me a new required vector b. Here's an example. Suppose I have these three vectors, u1, u2, u3, given as follows, and b, the constant vector. Then if I can find a linear combination of these vectors, something times u1 plus something times u2 plus something times u3 that add together to give b, then that has the exact same solution as this matrix vector equation because of the equivalence that we just looked at. Because this says that x1 times the first column plus x2 times the second column plus x3 times the third column must be the b vector. But that's the same as the solution to the simultaneous linear equations. 2 times x1 plus 5 times x2 minus 4 times x3 equals 3, and also minus 1 times x1 plus 2 times x2 plus 6 times x3 must equal 2, and 3x1 plus 7x2 plus x3, 1x3 must equal 5. And you should check that this is the exact solution. Each of these cases, the linear combination of vectors, the matrix vector equation, and these three linear equations are only satisfied when x1 is 4 over 67, x2 is 45 over 67, and x3 is 8 over 67. The easiest way to check this is to put this matrix and this vector in your calculator and do matrix times vector, and you'll see that you get this result. Or it's easy to form the linear combination of columns by hand if you're fluent in fraction or rational arithmetic. But either way, you should convince yourself that this particular set of values of these three variables is the only one that satisfies these three conditions, which are all equivalent. So here's an application of matrix vector equations or vector equations. Suppose we want to balance the chemical equation where we have phosphine, phosphorus, and 3 hydrogens, some quantity of that plus some quantity of oxygen, which exists as O2, transforms, this is a burning when we combine something with oxygen, to give me phosphorus pentoxide, which is 4 phosphorus atoms with 10 oxygen atoms. These are both pictured here, and free up a certain amount of water. Well, we can use linear algebra to solve a system like this. We let the elements of a vector represent the number of atoms of each element in one particular compound here. So the first element in the vector will represent how many atoms of phosphorus we have, the second element how many atoms of hydrogen we have, and the third element how many elements of oxygen. So here in the first case it would be 1 phosphorus, 3 hydrogens, and 0 oxygens. So there's 1, 3, 0. For O2 it would be no phosphorus, no hydrogen, and 2 oxygen atoms. For my phosphorus pentoxide, there's 4 phosphorus atoms, no hydrogen atoms, and 10 oxygen atoms. And for my H2O, my water, there's 2 hydrogens and 1 oxygen and no phosphorus. So this is a vector equation. We could also write it in the following way as x1, x1 times the first vector u1 plus x2 times the second vector u2. Now notice I want to put these all on one side, so it's going to be minus x3 times the third vector u3, and then minus x4 of my fourth vector, u4, and those will have to add up to the 0 vector. That'll be my b vector, in this case, the constant vector. Well, it should be clear from either this kind of equation, it's not hard to balance, but it should be clear that the solution is I need one of these, so that means I need to come up with 10, at least 10 oxygens, but I need 4 phosphorus atoms, so that can only come by making this a 4. If I make that a 4, then I've got 12 hydrogen atoms, so this must be a 3, because I need to get, 3 times 4 is, so this must be a 6, because 2 times 6 is 12. But now I have 6 plus 10 oxygen atoms, so I have to have 16, so this guy must be an 8. So the only solution, well, the smallest solution with integer answers is 4 phosphines plus 8 oxygens gives me 1 phosphorus pentoxide along with 6 free water molecules. Now this we can sort of do by eye. For more complicated chemical equations, balancing chemical equations, we'll get to use the fact that this is a matrix vector equation and use matrix methods to solve it. So here's an exercise. Given the matrix A, which is 3 by 4, the vector of variables x, which lives in R4, and the vector of constants lives in R3, write the vector equation that corresponds to the matrix equation ax equals b. That's what linear combination of vectors do I need to produce b. And write the system of linear equations that corresponds to the matrix equation ax equals b. So please pause the video, work these exercises, and then when you continue the video, we'll reveal the solutions. Okay, hopefully you did that. Hopefully you didn't find those exercises too difficult. Let's compare answers. The vector equation is simply x1 times the first column plus x2 times the second column plus x3 times the third column plus x4 times the last column must be equal to the b vector. And the corresponding system of linear equations is given by doing the vector dot product idea. 13x1 plus 19x2 minus x3 plus 2x4 must yield 17. 6x1 plus 17x2 plus 18x3 plus 12x4 must yield 8. And the final equation is given there. 6 times x1 minus 4 times x2 plus x3 plus 19x4 must give minus 7. Okay, so hopefully you found those solutions, or at least didn't find this explanation too difficult. So for homework, please download and study the notes for Lesson 11, Matrix Vector Equations. And we'll look at those when we hopefully return to class on Wednesday.